This is what we learned on the third day of the unit, where we talked more about conditional probability. Specifically, we looked at problems that involve tree diagrams. So our first example says that a friend who works in downtown Austin owns 2 cars. 3/4 of the time she drives a small car to work, and the rest of the time she drives a large SUV. If she takes the small car, she usually has no trouble parking, and the probability that she makes it on time to work is 0.88. However, if she takes the SUV, she is at work on time with probability of 0.6. So a tree diagram is something we can draw to help us organize probabilities in this type of problem where we have 2 events, in this case, what car she drives and whether she's on time. And one event, in this case, the on time or not, depends very specifically on the first event, what car she drives. So this is when a tree diagram is really useful, when one event very clearly depends on the first event or another event. So the way I draw the tree diagram, which is what I'm going to do first, is I start on the left side of my page with these branches, and I'm first going to deal with my first event. So the first thing that happens when she wakes up in the morning, she decides which car is she going to drive. So she's either going to drive the small car or the SUV, and I'm going to assign what probabilities they have on the actual lines of my tree. So small car probability was, it says 3/4 of the time she drives the small car. So I'm going to put 0.75 on that branch. And if we just think simple math, we know that if 75% of the time she's driving the small car, that means 25% or 0.25 of the time she's driving the SUV. So that's our first little part of our tree diagram. Okay, so then the second thing that happens is she's either on time to work or she's not on time to work, and that depends on which car she drove. So I'm going to first start over here on the small car, and we have 2 branches coming off small car. She's either on time or she's late. The problem tells us that she drove the small car. Her on-time probability is 0.88, and that leaves us to think mathematically. That means the probability that she's not on time or late is 0.12. So just, we know that these 2 branches need to add up to 1 because that's 100% of the time she drives a small car, she's either on time or late. Okay. We're going to do the same thing for the SUV. For the SUV, when she drives it, she's either going to be on time or late. The problem tells us that she's on time for the SUV, she's on time 0.6, which leads us to believe that she's not on time or late 0.4. So then the next thing we want to do, and I'm still not to any questions on the actual problem yet, we want to make sure that we set ourselves up for success as much as possible. So what I'm going to do is I'm going to actually calculate 4 probabilities over here on the right side of the screen. Basically, there are 4 different things that can happen in this scenario with these 2 variables. So either she drives a small car and is on time, or she drives a small car and is late, or she drives the SUV and is on time, or she drives the SUV and is late. So what I'm going to do is I'm going to calculate those 4 probabilities. Those are and probabilities. We want one thing and the other. So I know I can simply multiply. Even though these things are not independent, this depends on that. These probabilities that we've included in our tree diagram are taking into consideration that dependency. That's what we were given in the problem, so we know we can go ahead and multiply because we've separated those out based on the first thing. So this first thing that's possible is that she is driving the small car and is on time. So for that, I'm simply going to multiply 0.75 times 0.88, which gives me 0.66. Okay. Second thing that can happen is that she drives the small car and is late. So 0.75 times 0.12 is 0.09. So the probability of small car and late is 0.09. Third thing that can happen is she drives the SUV and is on time. So 0.25 times 0.6, which is 0.15. So probability of SUV and on time is 0.15. And then the fourth thing that can happen is that she drives the SUV and is late. So 0.25 times 0.4 is 0.1 or 0.10. So the probability that she drives the SUV and is late is 0.10 or 0.1. Now all 4 of these numbers should add up to 1 because these are the only 4 things that are possible in this scenario. That's only 4 things that can happen. So those 4 things, those 4 numbers should add up to 1. If they don't, you did something wrong somewhere. So go back and check. So from that information, and if we set ourselves up nicely, if we draw out the diagram, include the probabilities, and take the time to find your for and probabilities over here, it's going to make answering the rest of these questions a lot easier. So for part A, we just want to know the probability that our friend takes the SUV and is late. Well, we actually already calculated that. That was one of our for and probabilities. So probability that she takes the SUV and is late is down here. It's just 0.10. So I'm going to rewrite that out in notation, but we've basically already answered that question. And again, we got that just by multiplying probability of SUV times probability of late when she took the SUV. Part B is saying probability that your friend is on time. So we just want overall, in all scenarios, what's the probability that she's on time? Well, if I go back and look at my 4 final scenarios, these are the only 4 things that can happen. There were 2 places, 2 occurrences of her being on time. One was right here, driving the small car and on time, and one was right here, driving the SUV and on time. Either of those things leads to her being on time. So this total probability that she's on time is basically going to be adding those 2 numbers together, because either one of those is going to end up with her being on time, which is 0.81. So 81% of the time she's on time to work. Part C says if she takes the SUV, what proportion of days is she late to work? So this is a given. This means that given she takes the SUV, so only talking about days where she took the SUV, what proportion of days is she late? So writing that in notation, we always put what's given after the line, and we want to know what proportion of days is she late. So probability of late given that she took the SUV. And we do have a formula. If we wanted to, we could use our formula, probability of late and SUV divided by probability that she took the SUV. And if I use that formula and filled in those numbers, the top part is one of our for and probabilities that we've already calculated. Right here. And then the bottom part was told to us in the original problem. Overall probability of being late or taking the SUV was 0.25. So I could fill those in and I would get the same answer, but I can also just look at my table and see, given that she took the SUV, so looking at this branch of our tree, we can see that the probability of being late is 40%. We can just look at our tree and get that same number. So overall, this probability is 0.4. Again, we can use the formula to get that number, but we can also just look at the table because we have that. But part D is a little bit different. Part D says, assuming she's on time, so given that she's on time to work, what's the probability that she took the small car? So notation, again, whatever's given goes after. So given that she's on time, right, we want to know the probability that she took the small car. So what makes this one a little bit trickier is that I can't actually use the tree diagram to find that answer. It's not going to be on there. So if I go back and look at my tree diagram, I don't have any one spot, any one branch of this tree that has all the on-time situations. They're kind of split up. So it's not going to be quite as simple as part C because I don't have that branch of the tree. I can't just look at it. So I am going to use the formula on this one. So our formula for given says on the top of the fraction, we're going to do the probability of both things. So small car and on time. And on the bottom of the fraction, I'm going to do the probability of what we're given, which is that she was on time. So small and on time was one of my for and probabilities that I calculated to start with, which is this one up here, 0.66. And then on the bottom, the probability that she's on time, we actually calculated that back up here on part B, where we got 0.81. So we know that that's what goes on the bottom. If we hadn't already done that, this is one where we had to look at 2 different things because there were 2 different places where she was on time, 2 different in-case scenarios where she was on time. So we had to add those together to get the total probability that she's on time. 0.8148. So if she shows up on time to work, there's an 81.5% chance that she took the small car.